Log on, tune in, find out. Another good idea from Cambridge.
Pleasure to welcome George Dassios, and we have a slight change of topic here. We're going to talk about neuronal current decomposition via vector surface ellipsoidal harmonics. So essentially this is going to be EEG and MEG mapping, I think. So, yeah.
I would like to thank the organizers that gave me the opportunity to come back to this amazing academic atmosphere of Cambridge. And today I'm going to talk about the electric and magnetic activity of the brain as far as the analysis of electro and magnetoencephalography is concerned. And during this I'll have the opportunity to show some mathematics that came out from this effort. Okay, let me start with some trivial things. Okay. So what's the problem? Now the human brain is a conductive material. It has 10 to the 11 neurons. Each one of them can be communicated with 10 to the 4th weights through synaptic joints with the neighboring neurons. And the motion of any ions along the axon of the neurons create a current. The current generates an induction current within the conductive medium, and then both currents produce outside an electric and a magnetic field, magnetic flux field. And in electroencephalography, we measure the electric potential on the surface of the scalp, and in magnetoencephalography, we measure the magnetic flux in a distance 2 to 3, maximum 5 centimeters away from the surface of the head with a squid. Okay, in both brain imaging techniques, we aim to identify the neuronal current generated by the neuronal current that gives rise to the recordings that we have. Okay, the main difficulty in both cases is that the induction current hides the original neuronal current, and that creates a lot of difficulty. But in any case, as a rule, this happens both to EEG and MEG. And we have to be aware that all these very nice color pictures that we produce from EEG and MEG images, they show what it can be seen, okay, what intrinsically can be seen. And as you see, the brain is a very complicated machine, and it's very hard to understand it, but then if it was much simpler, we would be very stupid to understand it anyway. So let me show some brief history here. Now the fact that there are currents within the conductor that cannot produce any magnetic flux outside was known to Helmholtz more than 150 years ago. But it was not until 1996 that Focus, Gelfand, and Slava, they wrote a very nice paper, and they identified exactly what part of the current can be seen from MEG. And then a few years later, in collaboration with a student of mine, we did the same thing for EEG. Now, in both of these cases, the geometrical model was a sphere, and the result was somehow strange in the sense that it was complementary. It means that you can prove from these two results that the part of the current that give rise to one technique is exactly the one that the other technique is missing. And but this is only for the spherical case. So all this discussion about do we actually need the MEG, which we have to take it with a squid which costs more than $3 million, or we can do okay with the EEG, which the machinery costs $1,000. So the result is that there is information that comes from MEG, so we cannot avoid the $3 million. Anyway, But what I wanted to say is that on the average, a brain looks like an ellipsoid with average semi-axis 6 centimeters, 6.5 and 9 centimeters. That gives you 1.5 liter in volume approximately. And all these results do not hold true for if you get out of the spherical case. So to try to see what happened with the ellipsoidal model, which is a more realistic model for the brain, you have to attack the problem on the vectorial level. And there you have the problem that you don't have enough machinery to deal with vectorial problems in ellipsoidal coordinates. So let's start from very trivial things to see how far we can go. Okay, now just for history, say that separation of variables that started with the work of Bernoulli, Lagrange, and Dalibert, and it was fully exploited by Fourier, gave rise to most of linear mathematics today. Special functions, eigenfunction expansion, spectral analysis, harmonic analysis, and so on. In any case, separation of variables provides the eigenvalues and eigensolutions that everybody knows how important they are, but you need linearity of the equation, you need simple geometry, and you need also a lot of luck, even for simple geometry like the ellipsoid. But then just think about, think about what vibration theory of anisotropic media, quantum mechanics, and physically realizable systems would be without spectral analysis today. Anyway, it is most effective way to fit exactly boundary conditions whenever they work. And of course, everybody knows that separation of variables splits the PDE into three families of ordinary differential equations, which are connected between them, parameterized by the two separation constants. And most of the time, almost all time, the ordinary differential equations we obtain, they fall into the Sturm-Liouville theory, either singular or regular. And from there, the separation constants become eigenvalues, physical states become eigenfunctions, and all this orthogonality, convergence, completeness, and everything come from general theorems. Okay, now, in the early 50s, in Princeton, Eisenhardt, Moon, and Spencer, they tried to identify all the coordinate systems for which Laplace and Helmholtz equations are separable. And they found that if you restrict yourself to systems that they have planes, 1 and 2 dimensional coordinate surfaces, then you get only 11 coordinate systems. And of course, the simplest one is the Cartesian, and the most complicated is the ellipsoid. Okay, now, what we usually do with vector problems, we find the always press the wrong button. Okay. We find the eigenvalues of the scalar problem, and then we expand its component, its Cartesian component of the vector problem, and we get an expansion of this form where the coefficients are vectors. And then we try to apply boundary conditions, which is either very hard or impossible to do it. Why is that so? It is so because the vectorial character of the equation is casted into the coefficients and not into the eigenfunctions that carry the geometry of the problem. Okay? So what we should do basically is try to find vector eigenfunctions and expand the corresponding fields. But this is not an easy task. Let's see what has been done in this area. In 1935, an electrical engineer at Stanford, Hansen, generated vector spherical harmonics in trying to solve an antenna radiation problem. And in the appendix, he gives some result how they are reduced to the case of Laplace's equation. So that's what he found, he introduced, and it's well known to everybody today. The interior Hansen function, he managed to find this expression here, which is a vector solution of the Laplacian, and then he defined the other two as the rotation of the previous one. So the second one is the rot of the previous, the third one is the rot of the second, and so on. And basically the same thing here with the exterior ones. The y is the standard scalar spherical harmonic with some constant there. Okay, now the introduction of these three eigenvectors was not as important as it was the introduction of these three, which are surface vector eigenfunctions in the spherical system. And you have this one here, which is the p function, which is radial. And you have the b and the c functions, which are tangential, because d is the surface gradient here. So this is the surface gradient, which is perpendicular to this. And this also is perpendicular to both because of the exterior product. And basically, these three functions, they are orthogonal. They form an orthogonal system, local orthogonal system on the surface, and you can use that to identify coefficients. Now, if you go back to the solid ellipsoidal, solid surface harmonics, they are generated in terms of this, they are written in terms of these PB, C, and PB functions. And then it's trivial to solve any problem in this form, because all you do is you take the function, you expand it into the vectorial eigenfunctions now, so you have only scalar coefficients, and then all you have to do, you go to the surface, the boundary condition, let's say for a Dirichlet problem, you go to the boundary conditions, you express everything of this in terms of P, B, C, and then by orthogonality you evaluate the coefficients. Simple as that. Okay. Now, and a similar approach can be done for a Newman problem. If you try to solve the same problem with the Cartesian form, it's impossible. You get huge systems. Some of them are infinite by infinite. Okay. Now, can we extend this to the ellipsoidal harmonic? Okay. In order to do that, you have to, since 1935, a lot of people have tried to generalize that to ellipsoidal harmonics, and you see in a while why we cannot have something like that. Half of this period I was involved too, because I'm thinking in terms of ellipsoidal problems since 1973. So, so what you do is you try to scrutinize very carefully what happened with the vector spherical harmonics. So you start with an orthogonal Calvinian system and a vector field that is expanded in this form here, and you talk about the vector Laplacian, which is this equation. And of course, separation of this, it means to get a PDE from each one of the scalar coefficients. Okay, now, detailed theory that comes mainly from Eisenhardt, Moon, and Spencer gives you conditions under which such a thing, vector eigenfunctions, can be done. The first one says that the metric coefficient has to be 1. Very demanding. The second one has to, the ratio of the other two has to be independent of the first one. And finally, the product of these two has to be either the first one square or a constant, or 1. Very demanding coefficient. No one of these coefficients far away from being satisfied for the ellipsoidal system. So that discourages everything. So the answer is that we cannot have vector ellipsoidal harmonics which are as good as the spherical harmonics. But then, if we look at this as a first approximation, we go to the next question, the next approximation, and ask what is the best we can do with the ellipsoidal system. Okay, we cannot do as good as the spherical, but what's the best we can do? Okay. Just for the sake of communication, I'll just wave my hands to tell you what the ellipsoidal system is, because I'm not going to give any details, because if you know the system, this is trivial. If you don't know, this is not the right time to understand the system. Is complicated enough. In any case, the basic thing is that when you have a spherical system, basically you have a center and the unit length, and that's all. If you have an ellipsoidal system, you need many more to fit an ellipsoid. First of all, you need 3 Euler angles to find the orientation of the principal axis. And then along the principal axis, you have three different distances. So you need the center, three components for the orientation, and 3 components for, it's a 6-parameter, say, system. And there are infinitely many. For every problem, it has to choose the appropriate one. It's not like the spherical one. Okay, this is the how they are connected. Also, forget it. Just go down here. There are 3 variables, the rho, the mu, and the nu variable. Think of rho variable as the radial one that identifies the family of confocal ellipsoids. The other 2 identify a family of hyperboloids of 1 seat and hyperboloids of 2 seats. And they basically, the mu and the nu, think of the mu and the nu as the theta and phi for the sphere that identifies a point on the ellipsoid. Okay, so these are the tangential ones. Okay, look at the metric coefficients. The h's you see here are some semi-focal distances that come out of the system, some constants of the system. But look at them. Each one of them has rho square, mu square, and nu square. So how can you add with these 3 so complicated metric coefficients, how can you satisfy the conditions you have before? Very far away from being satisfied. Okay. Again, for terminology, Lamé with some ingenious techniques managed to separate variables in this system and produces the Lamé functions and the product of Lamé functions that make the interior and the exterior ellipsoidal harmonics. If we stick to the product of the 2 that correspond to the orientation, then you have the surface harmonics. The Lamé equation is this one here that determines each one of the solutions, determine each one of the product here. It's highly complicated because you have already here 4 singularities plus 1 at infinity, 5 singular points. And this down here is the most difficult part. You see, when you go to the spherical system, for a particular n, one of the separation variables is n times n plus 1, the eigenvalues of the angular operator. Now, once you have the degree n, then the order goes from minus n all the way to plus n. And if you go to the next degree, you all have to add minus n minus 1 plus n plus 1, and that's it. The problem here is that you have again the same n plus 1 dependence here, but you have the second separation constant that plays the role of the mu here, which is, as you go from one degree to the next one, they all change. And they can be identified only by solving irreducible polynomials of higher and higher degree. So there is a limit how far you can go. By hand, you can go all the way to n equals 7, where up to this point, you can produce all the classes of Lamé functions by using solutions of 4th degree polynomials. But that's it. Okay. But in any case, most of the times, you never go so far, because with n equals 7, you have already 65, the first 65 eigenfunctions. Okay. Again, there is nothing much I can tell here. These are the classes, and just remind that these are the interior and these are the exterior, and the exterior Lamé functions, they are always given in terms of elliptic integrals. Now, back to our problem now, to the second approximation. So, what is the importance of the vector spherical harmonics? The importance is that you can produce the PBC, which are orthogonal, and you can solve problems on the boundary. Okay. What is the corresponding set for this one here? We know that does not exist. Okay, but let's pretend that it does exist and see what happened. In the spherical case, we have 1 radial and 2 tangential eigenvectors. Here, we try to do the same. We take 1 radial along the normal and 2 tangential by taking the gradient of the surface harmonic, and then again this thing here. Of course, complete orthogonality for this system, no matter what you do, you cannot achieve, because there is a theory that tells you that you cannot do it. So let's see what's the best we can do again. So in order to have some freedom, we take these three, the radial say, corresponding to radial, and the two tangential eigenvectors, and then you multiply with three scalar functions, and we leave the three scalar functions free to choose them in a way that you can we can identify as many orthogonalities, we can gain as many orthogonalities as we can. And there are 6 kind of orthogonalities for vector problems. There are three orthogonalities that have to do with the two different eigenfunctions, and then another 3 that are the same eigenfunctions with different indices, of course. So there are 6 of them. Well, after a long and tedious check-ins, we can find the first scalar function to be 1, the second one to be rho times h rho, and the third one to be rho, and choose this as a weighting function, this one here, and you get all the orthogonalities from 1 to 5. And that's optimum. You cannot do better because you cannot have 6. So the amazing thing is that you can get orthogonality for the 6th one if you change only the weighting function. So the problem comes that the orthogonality demands 2 different topological structures to get the complete orthogonality. And you have the same functions, the same scalar functions in front, but you have to switch to different things. And here it seems that it's very close to being orthogonal. But when you look at the conditions, it's very far from being orthogonal. That was the discouraging thing, for example, in the beginning. Now, okay, so that's the result, that complete orthogonality needs 2 different inner products. And in fact, the two weighting functions are connected through this. The ratio of the 2 weighting functions is the square of the metric coefficient that corresponds to the radial component here. Okay, here are the proofs of all this that I said before. And you have this bi-orthogonal now system, which of course depends on rho. Why it depends on rho and it's not rho free, radial free as it is for the sphere? Because the system is confocal, which means that since the foci, the 6 foci of the system are fixed, as you get bigger and bigger and bigger, the eccentricity becomes smaller and smaller, and at infinity you get a sphere. You don't see the differences between the foci. Okay. And of course, completeness is not a problem because every ellipsoidal harmonic is expressible in terms of spherical and vice versa. So you get the completeness from there. Okay, now, how can you use it to solve a problem? Okay, to solve a vector problem here, you just expand in the rho functions, in the d functions, and in the t functions. And then you pick up the first inner product, and you dot this with a rho function, so all these are gone by orthogonality, all these are gone by orthogonality, and since these are orthogonal between each other, you only get 1 coefficient. So the first sum is done. You can evaluate the first sum. Then you go to the second one. You dot with a d. All these are gone by orthogonality, all these are gone by orthogonality, this orthogonal 2, you get the b's also. Now, you go to the third one. If you dot with a t, all these are gone, but here, since these 2 are not orthogonal, you get the full series of the coefficients. Okay? It's very simple. All you have to do is evaluate this part, take 1, 2, 3 parts in one side, so express it in the component that is left, and then switch to a different topology and evaluate with the second inner product. Okay? So that's what you do. You evaluate, you have the function, subtract the 2 you can and then the third component lives here, and then you switch to the other one, and hence you can use the completeness. As a matter of fact, I don't know, but I haven't seen any other system that needs 2 different topologies to solve it. Let's go back now to the electroencephalography. Okay. Electroencephalography started with the recordings of Hans Berger in the 80s, but it became a mathematical theory in the 50s, and you have the direct problem where somebody is giving you the current and they ask you to find the surface potential, and the inverse is you measure the surface potential, you try to find the current. These are the governing equations. It's simple, and it is the direct problem is well posed, but the inverse, by lack of uniqueness, is not well posed. Okay, again, MEG in parallel. MEG started with the recordings of David Cohen with the first model of squid in 1968, and it became a mathematical theory in the 80s. Again, here, given the current, find the magnetic field outside, or measuring the magnetic field outside, find the current. The governing equation is this Dassios equation, and you see the magnetic field here is this part which is due, it's a volume integral, and is due to the primary neuronal current, and this one here, which is the secondary induction current that is distributed over dipoles over the surface by using, integral theorems. Okay, and again, direct problem is well posed, the inverse problem is not. Okay. For medical practice, people want to have information about this, what they call lead fields. For the mathematician, this is basically the lead field for the electric potential. The electric field is something like the Green's function for electroencephalography, and for the magnetic field is the Green's function for the magnetoencephalography. Basically, is that if you take a dipolar source, a dipole at a point r naught with moment q, then the electric field is written like that. So it's the value of the moment enters linearly. So you can isolate the moment, and you are left with the other one, which is this dyadic field here at second rank tensor here, which depends only on the geometry of the conductor, the geometry of the body, of the brain. And you do the same thing with the B here. So the LE is the dipolar electric lead dynamic dyadic observed at rho, and so on. Basically, they measure how sensitive are the electric, magnetic, and magnetic measurements at a point if you move the source. And that's why it's important for the medical applications. Now, let's try to solve now the EEG and MEG problem and see what happened. Okay, of course, this takes, you start here with the reference ellipsoid as the brain itself, and you can find the solution, which is in this form. And if you go to the lead field, it's written like that. Now, it doesn't look, there are different colors, but it's not clear here. But in any case, this is the lead field for the electric field. This part here is red. It doesn't see red. And is the part that depends on the source. These fields here, this and this part, are blue, and they are the field variables. They depend on the observation, of the point of observation. Okay, it's much harder to solve the corresponding MEG problem for the ellipsoid, but in any case, again, this part here and this part depend on the source, and the coefficients here are these integrals. Complicated integrals, but that's what they are, constants. So again, this is the lead field for the magnetic. Okay, now, you see, in both cases, you have the gradient of the interior and the gradient of the exterior ellipsoidal harmonics. So, by doing some calculations here, you see that the gradient of the interior is expandable in terms of the rho and the d functions, not t dependence. If you go to the exterior, again the same, rho dependence and d dependence. That means that no matter if you measure results from take recordings from electroencephalography or for magnetoencephalography, the t dependent on the field never appears. So this has not been incorporated into the way you pick up measurements in EEG and MEG yet. In any case, in both cases, no T dependence for the fields, not for the current, for the fields. Okay. Now we go to the red parts where we have the current. Okay. The current enters through this one, which is already, I show you, that depends only on rho and D. That means that EG has no T dependent of the current. So if there is a T dependent, this is silent. You can never identify it outside. And then for the magnetic field, this is not the case. All components appear. So consequently, there is a part of the neuronal current that is visible only through the MEG measurement, not the MEG measurement in this case. Okay, here I want to emphasize that the fact that we know in which subspace spanned by the R, the D, or the T eigenvectors we are identify the current, that does not mean that we have the whole component there. Only projections of that component we can have, and that creates a lot of problems because other decompositions give different interpretations and so on. Anyway, okay, let me go to the future now. What can be done here? By now we know that there are various decompositions of the current that reveal different aspects of EEG and MEG techniques, but can we identify exactly what component in every subspace is visible outside, intrinsically visible, not depending on the method, not depending on anything else? That we don't know. Also, we don't have good results about the sensitivity of the current localization in variations of the geometry of the head. Not stability in terms of measurements, but stability in terms of changes of the brain, geometry of the brain. Not all brains are equal. This is well known, of course. Of course, this one here, what is the support of the current that corresponds to a particular EEG or MEG recording according to Albanese and Monk condition? What is this, the Albanese and Monk condition? 3 or 4 years ago with Thanasis Fokas, we were trying to solve this problem. Take a sphere, and let's say that only at some point there is a spherical region that is excited. Use the direct solution and see how can I identify the center and the radius of the part of the current that is excited. After a lot of work, we identified the center, but we could not identify the radius. No way, for months. And then, as we were trying to solve this problem, this Albanese-Monk paper came out in inverse problems, and it proves that if you have a three-dimensional current, it's impossible to identify the support. Why is that so? Because the fields and the current live in dual spaces. If one operator identifies the field sites outside, the adjoint operator identifies the current. And since they are defined through integrals, you cannot identify from where the value comes. But they prove that if the dimensionality of the support is less than 3, if you have distribution of current on surfaces or on lines, then you can identify it. That's why we could not find the radius. It was impossible somehow. Okay. Now, furthermore, besides this here, the introduction of the vector spherical harmonics in 1935 provided significant freedom in solving boundary value problems, spherical geometry. And of course, the present introduction of vector ellipsoidal harmonics, which are much more complicated, identify an area of classical applied mathematics that is open to many theoretical questions as well as solution of real problems. Thank you very much.
Questions, please. So you mentioned in the head that I think the semi-axis was 6 and 6.5.
That's right.
If two of the semi-axes are the same, does those
identify? Oh, there is difference. There is difference because then it becomes a prolate spheroid. Yeah. 6.5 is this direction. 6 is this direction, and in this direction is the 9. but this is averages. I mean, they play, but usually they don't believe. What?
The point is they're different.
They are different. They are different, and this 0.5 of centimeter makes a lot of difference in mathematics.
Can I just clarify something for people not familiar with EEG imaging? So the result that you mentioned, if the current sources lie on the surface, then you can identify.
Not on the surface, not on the surface of the brain. It could be anywhere inside, but the support should have dimensions 1, 0, 1, or 2, not 3.
And in the medical application, do the sources lie on the surface somehow, like the brain? Or
On the surface of this membrane, of the grey cow. That's right.
Curvy.
That's right.
Any more questions?
But there's also deep, so-called deep sources.
That's right. This comes from the indentations that they go.
So is there any chance of identifying deep sources?
The main problem with the deep sources is that there's a lot of attenuation until you get out. And in fact, if you are in the, it is well known that if you have a sphere and you have a dipole which is radial, you can never get something outside because this creates magnetic field, magnetic lines which are tangent to the surface, and nothing comes out. Now, if you intend it, then there is field that comes out.
This is MEG.
But MEG, right? But if you go, as you go closer and closer to the center, they become more and more radial. In the center, everything is radial, so nothing can be identified from there. But if you are in the ellipsoid, well, for the ellipsoid it's different because the ellipsoid does not fall down into one point; it falls down into ellipse. So the dimensionality of the coordinate surfaces is the same with the dimensionality of the zero of the starting point, the focal ellipse as they call it. So if it is on the focal ellipse but not in the center, probably you can identify it, but I have to look at it.
No more questions? Or thank the speaker again. Thank you.
Thank you.